Okay, so if we want to describe the sphere in cylindrical coordinates, well, we start with polar coordinates in the plane, and we've already seen how to do that. And I'm not writing out all the detail in the partition, but we understand it implicitly. Okay, and we determine, very similar to the way we did this. Well, if we again just do, boy, that's a biggie. We just do this, and this is our R. Well, then our coordinate here is R. Our hypotenuse at the limit, at the boundary of the sphere is R. Okay? And this is the square root of R, big R squared minus little r squared, giving us okay. Well, what about spherical coordinates? See if you can write it down in spherical coordinates. Oh yeah, well, what's our typical increment? Our typical increment is not a rectangle, but it's an approximate rectangle. Because remember that we really have, in polar coordinates, we really have arcs here and not quite parallel lines here. Now I've exaggerated because, of course, as your increments get very small, you won't be able to distinguish between this and a rectangle. Now we've already talked about that.
Are we looking for the increment of volume?
Well, yeah, but I thought I'd maybe start with the polar region. Okay, so since you asked, what do you think we got to do now? First of all, well, I want to talk about what this is. Remember that the area of this is and I've used ends here because that's the way I'm used to writing it, but this is Z, P, I, J, just like before, right? Okay? So if we're given I in the R increment, you have, thetas. Now you could, well, that and other things you can do, but you can worry about that, okay? And then you have this, and the subscripts have to always refer back to what you had before. Okay? So you have R, I, delta theta, I, J. And remember, that's the length of the arc at your sample point, right?
They don't depend on I, do they? Because the theta's independent. The limit's on theta.
Yeah, I'm being careless. Theta is not necessarily independent. I'm doing the most general case. It can be independent. So you could just use a single M here. But maybe when you get to the outer rings that you get for your R increment, you want more division on your thetas. So we want to leave the door open to do that, okay? If you're doing approximations and you want your most efficient algorithm, you would make the number of theta divisions, you would have more theta divisions for the bigger R's.
Something like logarithmic, are they?
It may be just linear, okay? Your number of divisions being linear. But maybe logarithmic, and that's a good thought. Maybe some other function, depending on how your algorithm runs and all kinds of stuff, okay? And we're not, we're not getting into that here. I'll just kind of mention it to tell you, to justify why we want to maybe have M depend on which R increment, okay? And of course, these are RIs, okay? And these are theta J's. And Z I should put I's in these. And I should put I, J's on these. Okay, it's getting a little sloppy, but to, to be rigorous and to continue with what I was saying, you want to do that, okay? But really, I kind of want to cut to the chase here, although we've got a little bit of time left. Here's our typical increment, right? So this is our delta Ri, okay? And this distance here would be our Ri delta theta Ij, okay? So our area is Ri delta theta Ij times delta Ri. Although we would often write that in a little different order. I wrote it this way just to show this is this dimension, this is this dimension. Okay? Now what do we have to do to make this into volume increment? Well, our Z's, our partition will have a typical Z Ijk, right? Or a delta Z Ijk. Where's that going to go? Well, that's going to go here. So there's this, and here's your delta Z Ijk. So your volume increment is Ri delta Ri, delta theta, Ij, delta Z, Ijk. Okay? Looks a whole lot like this. Except you gotta have that Ri for the Ri delta theta to get this dimension. Okay? Now, you want to think through what you do in spherical coordinates. Let's see how we use this.